Now we look at the derivatives of the inverse trig functions. Derivatives of the inverse trigonometric functions. Derivatives of the inverse trigonometric functions. And these will be derivatives to add to your tool belt, such as knowing the derivatives of the trig functions. And for me personally, I never wanted to memorize these because I could derive them pretty quickly. But if you do memorize them, make sure you know them perfectly. And I'm going to show you how to derive them all here. So we're going to be using some implicit differentiation for this. So let's look at the derivative. Let's look at the derivative of, let's start with secant. Sorry. We're doing inverse trig functions, right? So let's look at maybe sine inverse. So if we let y equal sine inverse of x, then dy dx, if we were able to take the derivative of this, then dy dx would be the derivative of sine inverse of x. Okay? So by naming sine inverse of x y, we can think of the derivative of sine inverse of x as being the same thing as dy dx. Now, unfortunately, we can't simply differentiate both sides because we don't know the derivative of sine inverse. But what we can do is we can use the power of inverse functions generally to inverse both sides. So in other words, if y is the sine inverse of x, then you know that from your algebra and trig class that the sine function, the regular sine function of y, is just x. So we just inverse everything like that. And this we can work with. We can differentiate the sine function because we know the sine derivative. And we can go about finding dy dx because y is sine inverse of x. We can find dy dx here implicitly. All right? So what we're going to do is we're going to differentiate both sides with respect to x. So we inverse this equation because we can't differentiate. We get this one that we can. And then we go ahead and proceed to differentiate. Okay? On the left side, the derivative of the sine function is cosine. So the derivative of sine of y is cosine of y. But you have to use the chain rule because y is a function of x. So we have to multiply this by dy dx. So the left side derivative is cosine of y times dy dx. And the derivative on the right side of x is just 1. Thus, if I solve for dy dx, I can see that it's simply divide by the cosine of y. Okay? Now what I'd like to have happen is, I would like to, if at all possible, I'd like this to be in terms of x, because this derivative is derivative of y with respect to x. I'd like the derivative of sine inverse of x, right? So I'd like to replace cosine of y with something in terms of x. And so what we do is we come back up here to the original relationship that the sine of y equals x. We know that the sine of y equals x. And so that means that if our angle in a right triangle is y, let's call that acute angle y, the sine of that angle should be x. In other words, sine is opposite over hypotenuse, so my opposite side would be x and my hypotenuse would be 1. And then the opposite side would be x, hypotenuse 1, opposite divided by hypotenuse would be x. And so I've set up a right triangle that has this relationship. But in this relationship, I need to know the cosine of this angle y. The good news is both of these have the same angle y, right? So the cosine of y could be found by if I knew the adjacent side and the hypotenuse. Luckily, the Pythagorean theorem tells me that the adjacent side would be the hypotenuse squared minus the leg squared. And so I get the square root of 1, right? The square root of 1 minus x squared according to the Pythagorean theorem. So now what I can do is I can see that, all right, well, the cosine of y is adjacent over hypotenuse. And if I divide the square root by 1, I just get the square root. So cosine of y is just this square root. And so the conclusion here is that dy dx is this ratio, and y is the inverse sine function. So dy dx is the derivative of sine inverse. So the conclusion here, the big picture, is that the derivative of the sine inverse function is this algebraic function. There are no trig functions here, which is really fascinating, right? There's no trig functions in the derivative of this inverse trig function. It's just 1 over the square root of 1 minus x squared. And these types of things will be used a lot in calculus 2 at most universities. But that's your first inverse trig function derivative and how it comes about. Now the other 5 work the same way, so I'm going to move through those a little bit more quickly. The basic idea is start with an explicit equation, make it implicit so that you can differentiate the standard trig function and not the inverse trig function, and then solve for dy dx. And then take anything with y, use a right triangle to convert it to x in an algebraic form. Okay? So let's try another. Also, if you want to differentiate a sine inverse function, it doesn't just have to be of x. You could use this derivative rule along with any of your other chain rule, product rule, quotient rule, whatever. So keep that in mind. This is the most basic derivative of the sine inverse function. You know, in fact, let me go ahead and show you an example of applying the sine inverse derivative. So let's say find the derivative with respect to x of, how about x squared times sine inverse of e to the x. Okay? So here we have a product. So we have to use the product rule. So what we'll get is the first function, x squared, times the derivative of the second function, sine inverse of e to the x, plus the derivative of x squared, which is 2x, times the second function, so sine inverse of e to the x. Okay? So we still have to do one derivative. And this is a sine inverse derivative with the chain rule. All right, so I'll carry down my x squared. The derivative of a sine inverse function we just learned is 1 over the square root of 1 minus this thing squared. So e to the x quantity squared. Right? If this were just x, if this argument to sine inverse were just x, this would just be x squared. Okay? So this is the pattern for the derivative of a sine inverse function, but the input to this function, the argument to this function isn't x, it's another function. So I have to multiply this by the derivative of this using the chain rule. The derivative of e to the x is just e to the x. All right? Then we can copy the rest. So now if I just kind of clean up this first term, x squared e to the x will multiply on the top. So I'll have x squared times e to the x over the square root of 1 minus. When I square e to the x, that's e to the x times e to the x, which is e to the 2x, adding those exponents, plus 2x sine inverse of e to the x. And this, all of this, is the derivative of this product, okay? So I wanted you to see how you could use the chain rule, the product rule, various applications of this inverse trig derivative. Okay? The product of deriving the derivative formulas for these is just a way to remember the pattern for the derivative. Okay? All right, let's try another. Let's look at the cosine inverse function. And we're going to move more quickly now. And I won't do examples of all of them. We just did one. You have the idea of how to do that now with all your other rules. So now I'm just going to focus on how to get the derivatives of the inverse trig functions that we have remaining. So if I want to differentiate cosine inverse, I would start by calling it y. And then I would inverse this to say, well, then the cosine of y has to be x. Then I could differentiate both sides. Now notice I'm talking through this, but if you're taking notes, you should probably be writing in comments about what we're doing to both sides, showing some work here. But I inversed. Now I'm going to differentiate both sides. Now the derivative of cosine is negative sine. So I've got negative sine of y. But it's a chain rule because the input to the cosine function is y, which is a function itself, the derivative of which is dy dx. And the derivative of x is 1. Okay? Solving for dy dx, I'll divide by negative sine y. So I get a negative fraction, 1 over sine of y. Then I need to create my right triangle to write sine of y using x's. According to this relationship, the cosine of this angle y is x. In other words, the adjacent side divided by the hypotenuse should be x. So I'll use x as my adjacent and 1 as my hypotenuse. But I need the sine of y, which is the opposite over the hypotenuse. The Pythagorean theorem tells us that the opposite side should be the square root of the hypotenuse squared minus the adjacent side squared, or the other leg squared. So the sine of y is just the opposite divided by 1. So all I need is the opposite side. So I can come back over here, and I can replace sine of y with the square root of 1 minus x squared. So dy dx equals negative 1 over the square root of 1 minus x squared. So the derivative, so the final conclusion is that the derivative of the cosine inverse function is the same as the derivative of the sine inverse function with a negative coefficient. Okay, so that's another inverse trigonometric derivative. And it seems to follow that this is a co-inverse trig function, which with our regular standard trig functions, the derivatives of those co's are always negative, and this one seems to follow suit. So we'll kind of see if that continues to be true. Okay, so sine and cosine are done. Let's look at secant and cosecant. So let's look at secant inverse. So we'll say that y equals secant inverse of x, meaning that if you inverse that, the secant of y equals x. Differentiating both sides, the derivative of secant is secant tangent. So we've got secant y, tangent y. But I've got to use the chain rule because the input to the secant function is a function itself. So the derivative of y is dy dx equals the derivative of x is 1. Again, all I'm doing here is differentiating both sides. I'm turning it into a differential equation so I can figure out what dy dx is, because that's going to tell us the derivative of secant inverse. All right, dividing both sides, I see that dy dx equals 1 over secant y times tangent y. So now I need both of these, secant y and tangent y, to be in terms of x. So let's go look at our right triangle. I know that the secant of the angle y is x. Well, that's the same thing as saying that the cosine of y is 1 over x. because secant and cosine are reciprocals. So the cosine of this angle is 1 over x. So my adjacent side I'll use as 1, and my hypotenuse I'll use as x. Now the other leg will be the square root still of the hypotenuse squared minus the leg squared. Okay? So now we can come back and we can replace secant of y with, well, secant of y is x already. It's hypotenuse over adjacent, if you will. So we have 1 over secant of y is x. And then the tangent of y is opposite over adjacent. So the tangent of y is just the square root of x squared minus 1. So it's quite a bit different than sine or cosine inverse, but it's also got some similarities. It's a purely algebraic derivative. There's no trig functions. So what we see then is that the derivative of secant inverse is 1 over x times the square root of x squared minus 1. And again, this doesn't have to be x. If it were some other function, you would use the chain rule, and all these x's would turn into whatever that function is, depending on what it happens to be. Okay? So that's the derivative of the secant inverse function. Now let's look at cosecant inverse, and I'm guessing you can see that it's going to be similar. But let's work out the details. And I hope you're comfortable with these triangles. We're using very basic trigonometry here. It's a great review of some basic trig if you have forgotten. But let's look at cosecant inverse. I also recommend practicing with the concept of finding these derivatives in this way. That's a great application of implicit differentiation. So now we're going to say that y equals cosecant inverse of x, which means that the cosecant of y will be x. We'll differentiate both sides. The derivative of cosecant is negative cosecant, cotangent. Of course, argument is y to both of those, but the chain rule says we have to multiply by dy dx. And the derivative of x is still 1. Thus, dy dx is going to be negative 1 over cosecant y cotangent y. So we'll go look at our right triangle to figure out how to write cosecant and cotangent of y in terms of x. We know that the cosecant of y is x, which means that the sine, reciprocal, the sine of y is 1 over x. So opposite, we'd use 1, and hypotenuse, we'd use x, which would mean by the Pythagorean theorem that the other leg is the square root of hypotenuse squared minus the other leg squared. Thus, dy dx equals negative 1 over cosecant of y, which is just x, you could also tell from the triangle, times the cotangent of y. Cotangent would be adjacent over opposite, so cotangent would just be the square root of x squared minus 1. And so you see the similarity of the cosecant inverse derivative to the secant inverse derivative. And it seems to be true, again, that we've got a co-inverse trig function resulting in a negative coefficient derivative. So the derivative of cosecant inverse of x equals negative 1 over x times the square root of x squared minus 1. And we've got 4 of our 6 inverse trigonometric derivatives done. Let's finish off the last 2, the tangent inverse trig functions. Okay, so let's look at tangent inverse. So we'll call y tan inverse of x, i.e. tan of y equals x. Differentiate both sides. The derivative of tangent is secant squared. chain rule says multiply by dy dx. The derivative of x is 1. Therefore, dy dx equals 1 over secant squared x. Okay? So we can come back now, look at our secant squared of y. If it would have been secant squared of x, we'd have been done because this derivative would have been in terms of x. But it should be secant squared of y. So now we come back, we look at our right triangle. The tangent of this angle y, the tangent of y should be x. So opposite over adjacent, x over 1. Meaning the hypotenuse will be the square root of this leg squared plus this leg squared. And so the secant of y would be hypotenuse over adjacent. So the secant of y would be the square root of x squared plus 1. So dy dx equals 1 over the square root of x squared plus 1. But then so secant of y is that square root, but then we have to look at secant squared. In other words, we have to square this. And rather than write one more step here, the square is going to cancel the square root, so we can see that the derivative with respect to x of the tan inverse of x function is 1 over x squared plus 1. So that's kind of nice. The tan inverse derivative doesn't involve any square roots at all. Okay? The other 4 inverse trig function derivatives you see had a square root, and within the square root you had a minus. The difference is when you're doing tan inverse, you end up using the hypotenuse rather than one of the legs. And you get the hypotenuse by adding. Okay? All right, so that's the tan inverse derivative. At this point, I would bet on you being able to do the cotangent inverse derivative yourself, so I'd encourage you to pause the video and try it out to see what you get. You may even be able to guess it, but let's stick to the mathematics and ensure that we get it right, and then maybe you could come back and check your work. So cotangent inverse. Inverse both sides, so we get cotangent of y equals x. Differentiate both sides. The derivative of cotangent is negative cosecant squared. Multiply by dy dx via the chain rule. The derivative of x is 1. So dy dx equals negative 1 over cosecant squared y. Which now I'll point out, there's a bit of a shortcut you can take here because 1 over cosecant is just sine. So 1 over cosecant squared is just sine squared of y. So that may be nice to keep in mind. A good reminder anyway. But we still have y. We need to come over here and figure out more about this y and its relationship to x. We know that the cotangent of this angle y is x. So that means adjacent over opposite. So adjacent over opposite should equal x. So we have x over 1. The hypotenuse of which would be the square root of x squared plus 1 squared. Okay? And so now, dy dx is negative sine of y quantity squared. The sine of y would be opposite over hypotenuse. Opposite over hypotenuse, but it's sine squared, so we have to square this whole thing. And once again, you can see if you square this, the square root goes away. And lo and behold, the derivative of the cotangent inverse function is negative 1 over x squared plus 1 after you square the fraction. And that is our final inverse trigonometric derivative. Practice deriving these a few times. You'll get really good at it. You'll get good skills with implicit differentiation. You'll get great review of your trig functions. And then you'll never have to memorize these, and you can apply them. For example, if you run into a problem where you need to know the cotangent inverse derivative in conjunction with any other rule, you would do this process first to get the cotangent inverse derivative formula, and then you would adjust it to fit your scenario with the chain rule or whatever it may be.